Hello. Here's a question about a stationary wave on a string. And the first thing we should probably do is just include the equation that describes this little system. And it relates the frequency to the length, the tension, and the linear density, or the mass per unit length, as I call it. So let's start with the cross-sectional area. That's going to be pi r squared, or pi d squared over 4. And if I plug that in, that's pi 0.3 times 10 to the minus 3 squared divided by 4. So for that one, I get a cross-sectional area of 7.07 times 10 to the minus 8. Now, to get the linear density, so this is the tricky bit, I suppose. Mu, the linear density, is the mass of 1 meter. So let's pretend we've got a meter of wire. And with a cross-sectional area A. So we're going to work out the mass of this meter length. That's going to be the volume times its density. And the volume is cross-sectional area times the length, which is just A. So as it turns out, the mass density is the cross-sectional area times the density. So I take my previous answer, 7.07 times 10 to the minus 8, and I multiply that by the density, 4,000, which is already in the correct units. So that gives me a linear density of 2.83 times 10 to the minus 4 kilograms per meter, which seems okay. Less than a gram, I suppose. Find the length of the string. Now it's just plugging it into this equation. So I'm going to rearrange it for the length first. That's a bit scary actually. So f squared 4f squared L squared equals T over mu. So mu equals T over 4f squared L squared. Right, let's give that. No, oops. Okay. Dear me, that was. Okay, let's try and get this properly done. Okay, so. Sorry. Okay, so sorry, just got to get L. That's much easier. So 1 over 2f times root T over mu. Okay. So I'm just going to try and put that in using my mu that I calculated earlier. So 1 divided by 2 divided by a frequency of 50 times the square root of the tension, which is 0.8 times g, divided by the mass per unit length, which I worked out earlier. And I get 1.67 meters.